Every traveling salesman problem can be represented by a complete graph. And a complete graph is guaranteed to have Hamilton circuits. In fact, it's going to have many of them, n minus 1 factorial of them. When solving a traveling salesman problem, we are looking for the optimal solution. The optimal solution is going to be the Hamilton circuit with the least total weight, or perhaps if you want, you can think about that as being cost, but we might be tracking distances and things like that, and we don't always track money. So that's where I try to use the language of weight. So an optimal solution is going to be the Hamilton circuit with least total weight in a traveling salesman problem. Now, as a reminder, all TSPs or traveling salesman problems can be represented by a complete weighted graph. So as a reminder, complete just means any two vertices have one edge connecting them, and weighted implies that on all the edges are going to be associated weights. Now the first algorithm we're going to look at to solve traveling salesman problems is called the brute force algorithm. So let's go over the steps to solve this. So first off, given the problem scenario, we're going to represent it with a complete weighted graph. Alright, so since it's a complete graph, it will have Hamilton circuits. Step 2 is to list all the possible Hamilton circuits. Now, as a reminder, there is n minus 1 factorial of them. So this is sometimes no small feat as the number of vertices in the graph get larger. So that's what step 2 is. List all of the possible Hamilton circuits. So for step 3, now that we have all the different Hamilton circuits, and since all the edges have weights, we are going to determine the total weight for each Hamilton circuit. So since we have listed all of the possible Hamilton circuits, and then we'll have found the weight for all of the possible Hamilton circuits, then for step 4 we can identify that optimal solution. So the optimal solution is that Hamilton circuit of least total weight. Now a couple of disclaimers before I move forward. Okay, so there will be n minus 1 factorial Hamilton circuits. When we talked about for the counting argument that we cared about direction. So we started pairing the circuits in terms of their mirror images. So a circuit's mirror image would grab the same edges, it just travels them in the opposite manner. Because it grabs the same edges, it will have the same weight. Okay, so when we go to find the weight of the Hamilton circuits, if you can identify those mirror images, so we'll call it a mirror image circuit, then you really only have to find the weight for half of the possible circuits, because then the other half will be the mirror image and it'll have the same weight. So then we'll only have to find the weight for, so this gives us the counting argument for how many there are total. We'll just have to find the weight for half of them. Alright, so that's going to be a nice thing. It's going to cut our workload in half. Now when we go to list all these different Hamilton circuits, then keep in mind then that the circuit and its mirror image will have the same total weight. So when we get down to identifying the optimal solution, there may be more than one. And actually there's no question about maybe. There will be more than one circuit that has that least total weight. So we're guaranteed for a circuit for its mirror image to have the same weight, but there actually might be other ones that go about different vertices but have that same weight. Okay, so that could happen. So there may be more than one circuit that has that least total weight. When you get down to identifying the optimal solution, I only need you to state one of them. So you don't have to state all of them that have that least total weight. So there's where maybe if you're working on a multiple choice question, there might be more than one that fits. You might have found more than one that fits, but in terms of a multiple choice question, only one of them would be listed on the list. So you could grab the circuit or its mirror image. When you go to state it, just if it's a free response question, you don't have to state both the circuit and its mirror image. You only have to state kind of like one of those flavors. Unless there's an extra requirement in the problem. So for instance, it says that you have to go to a particular vertice second before you come home. Then you have to make sure you state the circuit that satisfies those conditions. But you would have taken those conditions into effect when you went to go up here to list all the possible Hamilton circuits. Now that we have the steps for the brute force algorithm recorded, let's go ahead and see all of this in action. Okay, so I'm going to scroll down here to this example. So it says use the brute force algorithm to find the optimal tour, state the weight of the optimal tour, start and end at vertex A. So for this graph, I want you to notice that when we go to solve this using brute force, it's already represented for us as a complete weighted graph. There are 4 vertices, which means there's going to be 4 minus 1 factorial, or 3 factorial, or 3 times 2 times 1, or 6 possible Hamilton circuits. Alright, so now at least I know how many I have to find. So let's go ahead and list all of them. I could have A, then to B, then to C, then to D, back to A. Maybe I'll lock in these first 2 and I'll just flip-flop these 2 guys. So that's all of them, that's A and then to B. So how about A and then to C? So then I could have B and D next. And then back to A. So then I'll flip-flop these 2. So that's all of them that start at A and then go to C. And then finally I could have from A and then to D. So then I would have B and C to go to. And then I'll flip-flop those 2. Alright, so that's it. There's my 1, 2, 3, 4, 5, 6 Hamilton circuits. So now we're going to find the weight for each of these. Now as a reminder, if you can pair a circuit with its mirror image, you don't necessarily have to find the weight for both of them. So like for instance, this one's ADC, B, ADC. Okay, so these 2 are mirror images. So maybe we'll do this in a different color. So this would be ACD. Okay, that guy's right there. Those 2 are mirror images. And this is ADB. Okay, so these 2 are mirror images. So when I go to start finding the weights for these, then I don't necessarily have to find the weight for these mirror image guys. So I'm going to cross them out. So this one, and this one. Because if I find the weights for these guys, then those ones will have the same weight. So let's find the weight for each of these. So A to B is 30. B to C is 30. C to D is 12, and then D back to A is 15. So adding all those up, we get a weight of 87. Okay, for this next one, A to B is 30, B to D is 9, D to C is 12, and C back to A is 43. So that gives me a total weight of 94. And then finally this last one, A to C is 43, C to B is 30, B to D is 9, and then D to A is 15. I want you to notice that I am recording the weights in the order that I would have found by running through these vertices. This is what I would be looking for in your work, to be able to kind of follow along with what's going on and where you're getting your numbers. Right, so if we add those things up, we get 97. These mirror images routes would have the same weight. So this guy would have weight of 87, this guy's mirror image route would have a weight of 94, and this guy's mirror image route would have also a weight of 97. So for each of the 6 possible Hamilton circuits, we were able to find the weight for each one of them. So now that we know all of the different possible Hamilton circuits and all of their different possible weights, it's easy for us to state what the optimal solution is. Okay, so the optimal solution will be this one with the weight of 87. So A, then to B, then to C, then to D, back to A. Or, and you don't have to state both of them, but the other one that would be acceptable for you to state is its mirror image route. So that is the optimal solution, and then it says state the weight of the optimal tour. So this is then it has an overall weight of 87. All right, so that's what the brute force algorithm looks like. So we're going to find the weight of all the different possible Hamilton circuits, and so then it's going to be very easy for us to identify the one that has the lowest weight. However, there is a catch. Even though the brute force algorithm is known as an optimal algorithm, which means it will find that optimal solution, it is an inefficient algorithm. So that's going to be defined as an algorithm that the computational effort needed to carry it out grows disproportionately to the size of the problem. So we just solved a problem with, for instance, 4 vertices. Let's say the problem were to get up to, I don't know, 6 vertices. Okay, so if I have 6 vertices, then I would have, so let's maybe record this. So if n equals 6, I would have 6 minus 1 factorial, or 5 factorial. 5 times 4 times 3 times 2 times 1, that's 120 possible Hamilton circuits. That means if I were to give you a problem with 6 vertices, there'd be 120 Hamilton circuits that you would have to list. Now you only have to find the weight for half of this, right? So you have to find the weight for at minimum 60 of them, because of the mirror images, but then you have to sit there and identify where the mirror images are to make sure you're counting these 60 very unique circuits. So that's already a problem that goes beyond something I would give you. And then these number of vertices grow larger. This actually surpasses the ability of our fastest computers to date to be able to solve. Be able to run through all of the different Hamilton circuits and then find the weights for all of them to find that optimal solution. Because of this factorial and the number of Hamilton circuits, the size of this problem goes very fast, very quickly. So the brute force algorithm is called an inefficient algorithm. So at that point in time, when we have more and more vertices, there's where we maybe need to find other ways to solve it. So there's where we're going to start talking about efficient algorithms. Okay, so ones that to solve it would be reasonable given the scope of the problem. But then we're also going to talk about the fact that these types of algorithms produce what is known as an approximate solution. So if you want to know the optimal solution, the very, very best route with that least total weight to solve a traveling salesman problem, we're going to have to use this brute force algorithm running through these steps.